Okay, welcome to 8.4 Application of Logarithmic and Exponential Functions. Our first example is pulled mostly from the textbook, page 378. I think they have nearly the same examples. Maybe they vary just a little bit. The topic is earthquakes. So perhaps some of you have heard about this Richter scale before. When we're comparing sort of two things here, I'll move off to the side. M is equal to the magnitude of the earthquake on the Richter scale. Okay, so magnitude, some number on this Richter scale. While the A value, and you'll notice that there's two of them, that's the amplitude of the Earth's movement. Amplitude of quake. So you can imagine, so here's your ground. I don't know. You're going to stick a stick in the ground, and then the earth quakes, and the stick moves back and forth. Okay, the amount that it moves, this would be the amplitude. So it's going to be moving back and forth just a little bit. Clearly, they have very exact seismographs measurements, and suffice it to say that the Earth is always moving at least a little bit, right? There's never a zero amount of amplitude. So it's this Richter scale is comparing the amount of quake, of moving back and forth that the Earth is making during an earthquake compared to what they call here a standard earthquake. Now, maybe it's not a standard, maybe the word earthquake is an amount, so maybe standard background amount of motion. So if you just had a seismograph going off all the time, even when there is not an earthquake going on, they're going to measure some amplitude. They're going to measure some kind of motion all the time because the Earth is always a little bit jiggly. It's always moving a little bit. So the idea that this A0 is equal to, it's like the zero level of a Richter scale. So if we were to say, okay, on the Richter scale, you got two things. You've got your M, and then you would have your amplitude, the amount of motion that's taking place. So zero, from what I understand, the amount of motion you're getting is very, very small. You're getting like 1 micron, which is a millionth of a 1 times 10 to the negative 6 meters of motion. So it's hardly moving at all. So I experienced a couple years ago an earthquake in Myanmar, in Southeast Asia, of about 6.8. I don't know what the motion was, but we don't really describe it in how much it's moving around, but we talk about the amount of destruction it was. And there were a few people that died in this earthquake. I was okay. My family was all right. We were about 100 kilometers away from the epicenter, but it's pretty crazy amount of destruction that happened. Now, if I was to go up, say, one higher to 7.8 on the Richter scale, the amount of amplitude on this side, it would go up 10 times as much. And that's where the logarithmic nature of this takes place. Okay, so that when we move up one on the Richter scale, when we make m 1 larger, this goes up by a factor of 10, that we're multiplying by 10. Okay, so hopefully all this is just a bit of a background to help you understand the idea of what a Richter scale is and this logarithmic scale. In our first example, we're talking about in 1946 in Haida, Gwaii, I'm not sure how to say that, in Haida, British Columbia, there was an earthquake that measured that with an amplitude measuring 10 to the power of 7.7 times this background, this standard earthquake. Okay, so if I was to write this out, I could say, okay, here is some amount of amplitude in our earthquake in 1946. So I'm just going to keep track, because in our next question we're going to have one in 1949, and I just want to keep track of it. This is equal to 10 to the power of 7.7 times our background one. Okay, determine the magnitude of the earthquake on the Richter scale. So what that is asking is, what is m? So using our brand new formula here, we can say m is equal to the log of a over our standard earthquake, like this. So putting in our numbers, we get the log of, now instead of a, I can write, now this a here would be our 1946 one. Maybe I'll just add that. Okay, so this particular one we're interested in is the one that was in 1946. Now that one is 10 to the power of 7.7 times the standard one, divided by the standard one. Okay, so hopefully you can see where this is going. I can cancel these two out, and I can say m is equal to the log of 10 to the power of 7.7. Since it's not mentioned which log it is, the default is 10. Okay, and when I change this to exponential form, I get 10 to the power of m is equal to 10 to the power of 7.7. So m is equal to 7.7. And looking back, this is kind of how the Richter scale is designed, okay? If there's an earthquake that is 10 to the power of 7.7 times what a standard one was, that by definition, because this is just a straight log of that ratio, we get 7.7. So if you had something that was 10 to the power of 4 times of a standard, this one would be 4. Here, looking at our next question, we have one that's 8.1 times. Okay, so we have an earthquake in 1949, and it registered a magnitude of 8.1 on the Richter scale. So my m value will be 8.1. Or another way to say this is that the amplitude of this one in 1949 is going to be equal to 10 to the power of 8.1. times my standard. Okay, so that's just another way of looking at this Richter scale. Determine how many times stronger this earthquake was the one in 1946. Well, the one in 1946, that one had a Richter scale of 7.7, so that was 10 to the power of 7.7 times the standard. So that's how the logarithmic works. If some of you might be going, Mr. Speiser, you went so fast, where did that come from? Well, if we wanted to back up, we could say m is equal to the log of a over a0. And in this one, we're doing the one for 1949. We could say, okay, here the magnitude was 8.1. M is 8.1. It's equal to the log of a, the amplitude of the earthquake in 1949, divided by the standard one, and this is a base 10. So if I change this to exponential form, 10 to the power of 8.1 is equal to this ratio of the 1949 amplitude divided by the standard. So if I multiply both by the standard, then I get the amplitude in 1949 is equal to 10 to the power of 8.1 times my standard. Okay, so this is sort of in long form. That's how you can prove this statement right here. So now we're going to say, how many times stronger was this one than the one in 1946? How many times stronger was it? So really, when you're saying that, you're saying, what is the larger value minus or divided by the lesser value? Like if I said, how many times larger is 140 than 14, then you're really dividing it, aren't you? So in this question, they're saying, how many times stronger was this earthquake compared to that earthquake? So I can divide them out. Okay, so my answer is going to be equal to, if I delete that, equal the quotient of those two. So I will get these standard earthquakes will divide out, and I get 10 to the power of 8.1 divided by 10 to the power of 7.7, which when I divide powers with the same base, I subtract the exponents, so I get 10 to the power of 0.4, and then I'd have to get my calculator out, and 10 to the power of 0.4 I think is about 2.51. So you'll notice that this will not have units because it's asking how many times greater was this one. Okay, so again, just like my discussion about how earthquakes work, here we went from 7.7 to 8.1, and if it would have gone 1, like if it would have gone from 7.7 to 8.7, then just by definition, just by understanding how a logarithmic scale would have been, we could have said it would have gone up, it would have been 10 times as much. But since it only went up 0.4, the increase was 10 to the power of 0.4. And let's take a look at our next example, number 2, and we're talking about the pH scale. So those of you in grade 12 chemistry who are taking it this semester, or if you took it in a previous semester, you'll be familiar with this already. The pH scale is used to measure the acidity or alkalinity of a solution. It is defined as, and we use a lowercase p, capital H, is equal to the negative log of, you know what, technically we need to have the square brackets around H plus because those square brackets around like that have a meaning in chemistry, because that means the concentration of hydrogen ions. So this isn't mathematical parentheses, those square brackets mean concentration, where H plus, maybe we should go like this, where this is the concentration of hydrogen ions measured in moles per liter. A neutral solution, such as pure water, has a pH of 7. The closer the solution is to 0, the more acidic. The closer to 14, the more alkaline, or sometimes we use the word base or basic, acidic versus basic. All right, so a cola drink has a pH of 2.5, whereas milk has a pH of 6.6. So we got some cola maybe here, and we have milk. We can do some comparison here. This one has a pH of 2.5, and this one has a pH of 6.6. How many times acidic as milk is a cola drink? Okay, so when they're saying how many times acidic, they're not saying what's 6.6 divided by 2.5. When they're asking about how many times it's acidic, and the next sentence describes this, this is calculated by comparing the number of ions. So really what we're wondering about is what's the relationship between the hydrogen ions of one versus the other. Okay, so how many times as acidic as milk is a cola? So we want to do the hydrogen ion concentration of cola divided by the hydrogen ion concentration of the milk. This is really what we're looking for. How many times more hydrogen ions of cola are there compared to our milk? So looking over here, we can say that this pH is equal to the negative log of the hydrogen ion concentration. And now I'm on the cola side here, so I'll just keep track of this. I'm going to write cola, and here I'll write cola. And so our pH is 2.5 is equal to the negative log of this hydrogen ion of cola. Since there's no other base put in, this means base 10. So before, though, I do my exponent, I should divide or multiply both sides by -1. So I'll put a negative here, and I'll make that positive. And now I'll change to exponential form. So 10 to the power of -2.5 is equal to the hydrogen ion concentration of cola. Now looking over at milk, milk has a pH of 6.6, so it's going to go very similarly. We're going to say the pH of milk is going to be equal to the negative log. We're running out of room here a little bit. Let's see if I can try something fancy here. Just move this over a little bit. There, it kind of worked. Negative log of my hydrogen ion concentration of milk. My value is 6.6, so I'll put 6.6 is equal to this negative log of, I'll write it all out again, of milk, and multiply both sides by -1, so this becomes negative, that one becomes positive, and now I'll say 10 to the power of -6.6 is equal to my H plus concentration for milk. Okay, so what does this mean? Looking at our values, 10 to the power of -2.5. Well, it's kind of be nicer. Let's just pretend for a second that it was 10 to the power of -2. So that would look like 0.01, right? Let's just pretend for a second this was -10 to the power of -6. So that'd be 0.000012345, like that, okay? The concentration. There's way fewer hydrogen ions floating around in the milk than there are in the cola, okay? So when we look at how many times more acidic, if we just had these nice kind of values, it'd be easy to calculate. We have to get our calculator out. So you can, just by inspection, you're going to say, hey, there's way more here than there are here. Okay, and this is the nice thing about the logarithmic scale. 2.5 and 6.6, they're much more manageable to get a sense of. If you had to deal with these big decimals, it'd be harder to get a good sense of how acidic something was. So we plug in our numbers here. So this value, H, the hydrogen ion concentration of cola, that is my 10 to the power of negative 2.5, divided by the hydrogen ion concentration of milk, 10 to the power of negative 6.6. That's where you get your calculator out again, and I think my value is about 12,589. So how many times? This many times more acidic. Okay, here's another question. An apple is 5 times, I'm just going to pause for a sec. All right, sorry about that. An apple is 5 times as acidic as a pear. So again, when we're talking about as acidic as, we're going to say the hydrogen ion concentration of an apple is 5 times the hydrogen ion concentration as there is in a pear. So when we write that out mathematically, we can say, okay, the hydrogen ion concentration of an apple, I'll just put an A for apple, is 5 times as acidic as a pear. So the hydrogen ion concentration of a pear, P for pear. If a pear has a pH of 3.8, okay, so the pH of a pear is equal to 3.8. So if I go here, negative log, H plus, and this is pear, so I can say 3.8 is equal to the negative log of this hydrogen ion concentration of a pear. So again, multiply both sides by negative 1, and this is a 10. So 10 to the power of negative 3.8 is equal to the hydrogen ion concentration of a pear. Determine the pH of an apple. Okay, well, maybe I'll switch to green because I'm writing so much here. The pH of an apple is going to be equal to the negative log of the hydrogen ion concentration of an apple. And how do I figure out the hydrogen ion concentration of an apple? Well, it's pretty straightforward. I put it from this first line over here. The hydrogen ion concentration of an apple is equal to 5 times the hydrogen ion concentration for a pear, and I already figured that out. So here I go. pH of the apple is going to be equal to the negative log of 5. I'll substitute this one in here. 5 times 10 to the power of negative 3.8. Okay, so just to review, how did I figure that out? I took this value here. It's the H plus hydrogen ion concentration of an apple, and that's exactly what this is. It's the same notation. Hydrogen ion concentration, here I just wrote A instead of apple, that is equal to 5 times the hydrogen ion concentration of a pear. That's exactly where this comes from. So 5 times 10 to the power of negative 3.8. So finishing this up, I would get my calculator out. Oh, first I guess I should go and write pH of an apple is equal to, so this is the part where I get my calculator out, and I would say that negative times the log of, and then figure out this 5 times 10 to the negative 3.8 is equal to, now did I do my calculator work already? I think my answer is about 3.1. That's what I get for a value. So you're going to get a negative value when you do this log times, and then this negative will make it positive again. Okay. Here we're doing an example with sound, and it's very similar to our earthquake one, where we have some sound of intensity I compared to I sub 0, where in this case we call it the threshold of hearing. Maybe that would have been a better definition for earthquake instead of standard earthquake, say the threshold of measuring an earthquake. So I over I0. The only difference here is that we have a 10 in front. And you'll notice that the scale has a decibels in it. So this deci, that's where this 10 comes from. So unfortunately, we're using a decibel system instead of a bell system. It kind of would work better. So you're going to use this Greek letter beta for the bells. So there's two things that we're comparing. Remember that this value here, this is decibels. And then we have this I, which is sound intensity, with some pretty crazy units. The units are watts per square meter. So again, when since it's a logarithmic scale, the sound intensity can get this can turn into a very large number. But because decibels are measured logarithmically, they are quite manageable. Okay, so here we're going to see some examples here. The first one says, it is strongly recommended a person wear protective ear gear when the sound intensity is 85 decibels or greater. The MTS Center measures 110 decibels when the Jets score a goal. How many times louder is the MTS Center than the recommended maximum sound density? Okay, so let's just think about this last statement there. How many times louder is the MTS than the recommended maximum sound intensity? Are we comparing how many times more the decibels or are we comparing how many more times the sound intensity is? And you see these words here. So we want to compare how many times greater the MTS is, so the intensity of the MTS divided by the intensity of the recommended maximum. How should I do this here? Max. I got MTS over max. Okay, well, I hope that makes sense. So we're going to say how many times greater is the sound intensity at the MTS Center when the Jets score a goal. How many times greater is that compared to the recommended maximum? So we're going to have to find both of those values. Okay, so the MTS part, this is when we have 110 decibels. So getting out our brand new formula, here it is. So we have this B beta symbol is equal 10 times the log of, and how do they do it here? It's I over I0. And again, this is the threshold of hearing, so it's very, very quiet. And we have to figure out then what this I is. And if this is at the MTS, this is the sound at the MTS center. Okay, so let's put this, let's solve for, let's make it look like this. I equals MTS equals, and then solve for something here. And then we can do the same thing for our I max. Okay, so this number is 110 is equal to 10 times the log of I MTS divided by IO. We're going to have to make some more space here. Just erase that. Okay, so because of that 10 part, because of the deci in decibels, I can't do the exponential version yet. And just like before with pH, I had a negative there I had to get rid of. Now I have a 10 here I need to get rid of. So I'm going to divide both sides by 10. Like that, and because I'm running out of space, I'm going to cheat a little bit. I'm going to erase this, and then I'll erase this, this, and that. There we go. So now after I divide both sides by 10, I get 11. Now is the time that I can change to exponential form. So 10 to the power of 11 is equal to the intensity of sound at the MTS center when we score a goal compared to the threshold of hearing. It's a 1 with 11 zeros times more intense. Okay, so solving for I there, solving for the intensity at the MTS center, it's going to be 10 to the power of 11 times the threshold of hearing. Okay, I think I need to do a different color here, so I'll go blue, and now instead of MTS, we'll do the second one, which is the maximum recommended. Okay, so now we'll do the 85 decibel version. And so we'll say that again, B is equal to 10 times the log. And now this I in the numerator will be this maximum recommended amount compared to the threshold of hearing. So if I put an 85 into there is equal to 10 times the log of, again, this ratio. I won't write it out again. And I have to divide by 10 again. So I'll divide by 10 here and put a decimal in here. So this is to the base 10. So if I change this to exponential form, I get 10 to the power of 8.5 is equal to the recommended maximum sound intensity divided by the threshold of hearing intensity. So if I solve for this maximum, is equal to 10 to the power of 8.5 times the threshold of hearing. Okay, so now we're ready to answer it, and just like we had our original thing set up here, I have two answers for this, and luckily they're both in terms of the threshold of hearing. So the MTS center is 10 to the power of 11 times the threshold of hearing, and the maximum recommended is 10 to the power of 8.5 times the threshold of hearing. So this is 10 to the power of 11 times the threshold of hearing, and this is 10 to the power of 8.5 times the threshold of hearing. So these cancel out, and I'm going to get 10 to the power of 11 minus 8.5, which is equal to 10 to the power of 2.5, which is some pretty large number. I don't have it at my fingertips right now. Okay, checking on my calculator, it appears to be about 316 times. So is it recommended? No, it's not. So the only solace you can take, big Jets fans that like to attend the game and enjoy it when the Jets score a goal, is that at least that this 110 decibel level does not get maintained for a long period of time. When people are screaming like that, it might be a good idea to cover your ears for a second, or to wear earplugs or something like that. Our last example here, a truck emits a sound intensity of 0.001 watts per square meter. Okay, we don't hear this very often about watts per square meter. And for this question, we're going to have to use the fact that my threshold actually has a number attached to it. It's 10 to the negative 12. So we have two values here. We have the I of the truck, which is equal to let's convert this into 10 to the power of something. 10 to the power of negative 3. So this is the same thing as 10 to the negative 3. And our threshold of hearing is equal to 10 to the negative, what was it? I forget. Was it negative 12? Okay, negative 12. All right, so bringing out our excellent formula again, we can say that B, or beta in decibels, is 10 times the log of whatever the intensity that we're interested in this case, it's our truck, all divided by the threshold of hearing. So I'm going to say that this is equal to 10 times the log of, now I have in my numerator 10 to the negative 3, in my denominator 10 to the negative 12, that is a 12. 10 to the negative 3 divided by 10 to the negative 12 is going to be equal to 10 to the positive 9. So my next line is 10 times the log of 10 to the power of 9. So what's this part here? And you may have seen this pattern a few times, and if you kind of starting to get an intuitive sense of how logs work, you can say, oh, that's just going to be 9. But let's test it out anyway. So if I say, okay, y is equal to log base 10 of 10 to the 9. So this 10 is my base, so 10 to the power of y is equal to my argument, 10 to the power of 9. So therefore, y is equal to 9. So looking inside of here, I can say that this is equal to 10 times 9. So my answer is 90. So B is equal to, or my beta is equal to 90, and it does have units, and they're called decibels. So in the sense of how loud it is compared to the MTS center, 110 decibels, it's only 90 decibels, but still you got to be careful because 85 is where you've got to start wearing your protective ear gear. Okay, these can be a little challenging, so please do practice them. I know that the earthquake kind of question has been on provincial exams before, and they really love to do the pH ones, so please pay particular attention if there are any kind of pH questions in there. Thank you, and I will see you in class.